Excellent. So Tuomas will be talking to us about cantilever enhanced photoacoustics in gas sensing. Thank you, Tuomas.
Thank you, Geoffrey. This will be a quite general presentation, and actually I think the timing is pretty good because I've been doing photoacoustics for some time, especially with Professor Markko Vainio from University of Helsinki, and we have had discussions that maybe it would be time for a review article soon related to, let's say, recent advancements related to cantilever photoacoustic techniques and measurements and applications. But let's first start or rehearse some basic properties of photoacoustics. I think Stefan also mentioned this before, but it doesn't hurt to go through this again now. As has been explained, photoacoustics is not an absolute method, as many linear absorption techniques are, which essentially count the number of molecules in a given volume. In photoacoustics, the absorbed energy from the light causes local heating, and through thermal expansion, a pressure wave or sound is generated and measured. This is naturally, say, much more indirect method as compared to many other optical gas sensing methods. Also, photoacoustics relies on the sensitivity of the microphone or something similar to a microphone that will or can detect the pressure or the sound wave that usually requires a calibration, and the response is often a function of the used measurement frequency. Photoacoustics is also an emissive method, which is often quite beneficial feature in gas sensing, especially when measuring low concentrations of gases. On the other hand, photoacoustic signal is generated from example when the amplitude modulated signal hits the walls, I mean the interior walls of the photoacoustic cell, or the windows that will also generate a signal. And those are kind of unwanted background signals, but there's fortunately ways to combat this. Methods such as wavelength modulation, absorption spectroscopy quite effectively eliminate such background signals, and the actual measurement actually is very close to being truly emissive, also in practice and not just in theory. One of the most interesting feature, at least to me, of photoacoustics is that it is more or less wavelength independent, while many other techniques that, for example, rely on semiconductor detectors are not, but they're kind of limited by the wavelength region of the detector. One other important thing to note is that the photoacoustic, or the relation between the photoacoustic signal and optical power is linear. This basically means that in order to achieve the best possible sensitivity, the power should be as high as possible. Of course, it's good to keep in mind that the power itself it's not sufficient, but the power, if you will, needs to be directed at strongly absorbing spectral features to generate the acoustic wave in the first place. One actual drawback here, or in photoacoustics, is that the photoacoustic response can and often will depend on the composition of the gas, as gases have different thermal and acoustic properties. Another challenge is relaxation issues with some gases, which often lead to, let's say, reduced sensitivity. Fortunately, in many applications, let's say the gas composition is relatively stable, but this would be a problem if the carrier gases, if you will, would change drastically over time. So now on to what actually Gasera has been doing for some time already, to cantilever enhanced photoacoustics. So maybe it's good to still to remind that we're still talking about photoacoustics. It's just this we're doing it in a slightly different way, and the slightly different way is namely using a micro-machined kind of a saloon door uh, uh, microphone and an optical readout system to measure the position of the saloon door or the cantilever. So it's actually two things combined that make the good sensitivity. The thickness of the cantilever is in the micrometer scale, and the height and the width are in the millimeter scale. And that makes it actually it sounds like it's not thick at all, but it's surprisingly robust thanks to properties of silicon. And the other important part is this is especially where Professor Jyrki Kauppinen, the father of our current CEO, has done a lot of time over the years. It relates to very accurate miniature interferometers. So it is kind of funnily enough, we use another completely different optical technique to sense the position of the cantilever to be able to make very sensitive photoacoustic, let's say, sensors or detection platforms. One benefit in photoacoustic is that the dynamic range is very high. In some of our material, you can find numbers 10 to 5, 10 to 6, but a recent article that will hopefully come out soon from Tampere University or University of Tampere, I'm not really sure how it's called nowadays. They use different frequencies to kind of extend the linear range up to 10 to 8, which is quite a lot. And one other claim, some might consider this to be a bold claim, but we do claim that this cantilever-based photoacoustics is approximately 100 times sensitive than, let's say, conventional membrane microphones. And there's a couple of publications that you can check to verify these numbers. Okay, like I mentioned before, I will call this next part kind of like a mini review of some of the work that has been done and reported. And while I have your attention, I would like to thank all the authors on this list and many others who I've been working with over the years. There could be a few different structures to a review, but I decided to use the spectra figure I used in my earlier presentation as the backbone. And I will try to demonstrate to you that the wavelength independency claim will hold based on various examples directly adapted from these publications. And but please also note that the list does not include every interesting cantilever enhanced photoacoustic article out there, and I have left out, for example, some supercontinuum work and some FTIR work, because quite frankly, I haven't been that involved in those works or publications. So this is the same slide I used in my earlier presentation. I will start to go through the publication or concepts or works starting from the lowest wavelength that has been used and move up from there. This is a bit awkward. so looks like I cannot even make it to the x-axis. But this is quite interesting when it comes to let's say visible region, because it's not that often used in gas sensing. Nitrogen dioxide, which has been mentioned a few times already today, is an important molecule, and it has a wide absorption spectrum in the visible, roughly starting from 250 all the way up to 650 nanometers. So in that sense, I would say it's quite special compared to many other molecules. There are, of course, molecules such as oxygen that can be measured close to 760 using the so-called A band, but more commonly, laser-based techniques are used in the overtone region close to 1.5 micrometers. Maybe it's also good to mention that when we go through these examples and look at the spectrum, I mean, have a few words about the availability of light sources. 532 is it's green. The light sources, I mean, there's I mean, if you're looking for tunable DFB lasers, that's not going to happen. But there is certainly, for example, high power and very inexpensive LEDs, and but we decided to go with the almighty Verdi green laser. That's for anyone who doesn't know, it's I would say it's strictly a laboratory tool. The setup here, or the setup is very simple. So it's basically just turn on the light, guide the light through a lens, through the chopper into the photoacoustic cell, and start measuring. The numbers are actually are pretty good. So we were able to achieve a detection limit, root mean squared detection limit of 50 or ppt, or 0.05 pbb in 1 second with 4.7 watt of optical power. Of course, that's a lot of power, but like I said before, this is a laboratory system. However, I mean, I also have to mention, and by the way, I mean, all this publications I listed, most of them are open source or freely available. So please go ahead and read those if you're more interested in this. But we did observe water dependent behavior in the photoacoustic signal, where the response dropped by approximately 40% when we were measuring at very dry conditions. And the very dry here means that the absolute humidity was in the few hundred ppm level. It's time to move forward. So we start with 532. Let's move into the overtone region. This region has definitely been used extensively in optical gas sensing, and of course in telecommunication optics for sure. And there's a wide range of light sources and other high quality components available for this region. And this is also the go-to region for many cavity ring down system, and there are commercial cavity ring down instruments that use this very region to measure several lightweight molecules. And manufacturers are, for example, Tiger Optics and Picaro. The transitions in general in this region they're quite well isolated and still fairly strong, definitely to enable sub-PBB detection limits, or even sub-PBB detection limits. So this is actually now, I mean, some were probably expecting a presentation strictly based on photoacoustics, but this actually showcases that it's photoacoustics can be used together with many other techniques, many other optical techniques. So like I said before, and this still believe that it's this cantilever based technique. It's basically a sensor that's represented by the gray PA cell close to the middle of the on the setup figure. And in this very work, a cavity enhancement or a signal enhancement of about 100 was achieved, which is quite moderate, but still compared to many or another possibility would have been to build an external or internal multipass configuration, but the size or the diameter of the standard photoacoustic cell is 4 millimeters and the length is 90 millimeters. So it would be very challenging to build a multipass system with an enhancement factor of 100. I would say virtually impossible with those dimensions. The achieved cavity lock was pretty robust, which is essential, of course, for the experiment, as the photoacoustic measurement was performed in a wavelength modulation mode, as you can see from the figure on the lower right hand side of the slide. The sinusoidal modulation was at 30 hertz, and it was generated by moving the end mirror of the cavity to change the resonance frequency. And the laser was continuously locked to the cavity, and the laser was then following the modulation. For noise equivalent mixing ratio of acetylene, the system for the cantilever system with the cavity enhancement, the sensitivity was found to be around 240 ppt for 1 second integration time, and that was improved to 24 ppt with 100-second integration time. So I mean 24 ppt with 100-second integration time is definitely not bad. The Allen deviations that you can see, they do, I mean it's a different, I mean there's two plots that, or sorry, curves that are overlapping at low integration times. So one is without the cavity enhancement, that's the black one, and the other one is with the cavity enhancement. So at let's say low or up to 100 seconds, they are really similar, but then there starts to be some drifts because of the cavity enhancement that cause or it does not enable longer integration times to achieve better sensitivities. So let's move on. Next, we move to, let's say, to a region that is not that often used in gas sensing. It's still an interesting region, mainly because it has hydrogen fluoride, and hydrogen fluoride has very strong and well isolated transitions in this region. Otherwise, the availability of light sources is somewhat limited, and commonly used DFBs have pretty low output power in this region. So why I'm mentioning again this output power is because photoacoustic is the photoacoustic signal is directly proportional to the output power of the light source. But fortunately, OPOs usually can be tailored to operate at this wavelength region, and that makes the case of detecting hydrogen fluoride quite intriguing. And this is actually shows some of the work that was done. Like I said before, hydrogen fluoride is I would say its spectrum is very suitable for laser-based measurements, because there's really no significant interference from other species in this region, and the transitions are very strong. On the other hand, hydrogen fluoride, as was explained, is a very difficult gas to handle. The main challenges definitely in this work was handling of hydrogen fluoride and stability of the OPO. But once we were able to get hydrogen fluoride into the measurement cell and the OBO was working, the results turned out to be quite impressive from a, let's say, from a raw sensitivity point of view. So this would be 6 or 0.65 parts per trillion in 32 minutes. It's already quite a long time, but still it's sub PPT. There's a pretty large difference if you again look at the Allen plot, depending on whether the laser is on or off. And the blue curve is close to the, I would call this a technical sensitivity limits achievable with this technology. And in this case, the green curve shows the reality when we're measuring very reactive and difficult to handle gas, and also we're using OPO as the light source. That is usually not known to be the most stable light source out there. But still, either way, this the 650 parts per quadrillion sensitivity was indeed demonstrated with hydrogen fluoride inside the cell. So this is, I would consider, not a synthetic result, if you will. If you remember when I discussed about the NDIR example and the difference between NDIR and laser-based system in my first presentation, I used the broad illumination range to explain why NDIR suffers from interference. But with comms, it is possible to have, in a way, multiple of laser sources simultaneously, which can be used to measure a broad range of molecules with good resolution. So this is, I would say, a truly remarkable way of doing spectroscopy or gas sensing. So a comb can essentially combine the benefits of laser-based techniques with broad spectral coverage, and that is actually in what is needed in many applications to measure, let's say, more than a few gases at the same time. This work itself is quite different from the other examples I have, or I will show, because in this case the spectrum of radiomethane was not accurately known beforehand. Usually, I mean, the user or the community can use data from, for example, from Hydron or from other sources or publications to properly design and implement a measurement concept. But if you don't have knowledge of the infrared spectrum or a specific component, it's better to, or you're forced to measure it by yourself beforehand. Now that the spectrum is known for radiomethane, I mean, it would be possible to start designing maybe more sensitive laser-based systems for detecting radiomethane. This is the next one will be a bit different. At first, if we look at the spectrum, we can already see that when we started with single wavelength lasers. We had a comb, let's say a specific comb, and now I'm talking about an external cavity QCL or an EC-QCL. It is a versatile tool that is sometimes used in gas sensing applications. They are used to cover a broad tuning range, but a major drawback is that you can get or tune usually, well, always one wavelength at a time. So it's essentially one discrete laser that just has a really broad tuning range. And usually, I mean, in this case, the EC-QCL was operating in a pulse mode. That's usually not a good fit for really high resolution spectroscopy. And if it would be, often these can be these EC-QCLs operating in continuous wave mode, the tuning range is usually much more narrower. One other thing to note that this is, I mean, we're kind of moving from low wavelengths to higher wavelengths, and this EC-QCL covers pretty well the I would say that is the main fingerprint region for gas sensing, around 10 micrometers. You can find a lot of strong and isolated transitions of most molecules in this region, and moreover the region is relatively free from interference, for example from water, which usually has a huge impact, I mean a positive impact on the usability of this region. Like I said before, this is a bit different as compared to your, let's say, typical optical gas sensing, where you strictly use optical methods to build your system. And this work uses techniques more often found in analytical chemistry for sensing heavier molecules from a complex gas mixture. It has a clear benefit over direct measurement, but the downside, I mean, the clear benefit is that you actually can measure heavier molecules, which is here represented by eight hydrocarbons, and I would believe such a measurement, I mean, without the separation with any optical technique, when the gases are at fairly similar concentrations, would be almost impossible. If you disagree, just please let me know. The issues in this work, I think they were more like a technical issues, as they often are, but they were actually related to optimizing the sampling from the GC column. So we basically inject the sample into the GC column, and by using a temperature ramp, the GC column will separate the peaks, and the peaks will come out or of the system at certain times, as is shown in the lower figure. But the issue was that the gas volume, or the sample volume coming out from the GC column is very low. So we actually have to dilute or add air or buffer or carrier gas or buffer gas to fill the photoacoustic cell. So in a way, the sensitivity will be also diluted when we do this. And this is, I mean, it's good to remember that the effective volume of cantilever photo, I mean, in this system is around 2 or 3 milliliters, and that's still a bit too much as compared to what is coming out from a GC. And this will be the last one. I almost again fell off from the x-axis, but not quite. This last example uses what I would call, or some others would also call, long wavelength QCLs for detecting benzene. This region is a bit more, or much more exotic than many other regions, and there are not really many light sources that can emit at these wavelengths. And we were in a sense quite fortunate to be working with the University of Montpellier to get their experimental QCLs that were operating at these wavelengths. They could actually go a bit higher, I think, all the way to almost 20 micrometers with their technology. One interesting feature here is that usually, I mean, interference from water is a big issue in this region. It's interference from carbon dioxide. That's the major challenge. This is, I mean, it's a very simple setup. It doesn't get much more simple than this. There's a QCL that is wavelength modulated. Then there's a photoacoustic cell or a sensor, and a power detector for normalization. And the reason actually to do this work was to demonstrate that okay, we can use this system at long wavelengths, but we can also detect benzene, which is quite difficult gas to detect using optical means at sub ppb concentrations. And this is the last slide. So
okay, I just thought I'd ask. Okay, thank you.
Yeah. Okay. Yeah. Yeah. I know I'm a bit. Yeah. But this is the last slide. So I mean, just to showcase, or I added or included all the wavelengths that were used. Of course, there's something like 5.666 for formaldehyde that we use in our standard formaldehyde analyzers, commercial ones, but maybe that is not that interesting. I mean, scientifically. Then there's also one publication coming out for radiocarbon detection using 4.5 micrometers that I didn't have time or to include this in my presentation, and I'm happy about that because it's already too long. But I hope I have at least shown that the cantilever enhanced photoacoustic it's quite versatile technology, because it is, like I said, it's photoacoustics done in a slightly different way, and it is a truly wavelength independent or optically transparent, if you will. Yeah, and that's pretty much it. So I don't know, Jeffrey, do we have time for
I think
any
very
questions?
brief questions. Has anybody got a quick question for Tuomas? Otherwise, I think we should probably go into our lunch break, because we probably ought to allow ourselves fair time for that. Any questions? No. So are we all okay to start at 2 o'clock UK time, 3 o'clock Central European time?
Yes, so it's according to the program.
Yes, that will be back according to the program.
Yes.
Okay. Well, thanks, Tuomas, once again, and we look forward to seeing you all back at 2 o'clock UK time, 3 o'clock CET.
Okay, thanks,
Okay,
Jeffrey.
good. Right. Bye for now.